Okay, so today we're going to look at composite functions. This is a recap. This is something you have already done before. So say f of x equals 3x squared plus x, and let's just start with the basic stuff. Say I want f of 1. Well, you just substitute that in. 3 times 1 squared plus 1, and that gives you 4. F of a, so I'm just replacing all the x's with a. So it's just 3a squared plus a. Doesn't really do much, does it? F of 3x. So again, every x that there is in the original function, I'm going to replace it with what's in that bracket. So I'm replacing with 3x. And I've got, well, that should be squared, and 3x here. When I tidy it up, that's going to give me a 3 times, so that's going to give me 27x squared plus 3x. Be really careful with those brackets I put in here. This is a major issue that I've seen in some of your papers, that you don't put the brackets round, and you had 2x squared and you put that, oh, that's 4x squared, but you need to have that 2x in brackets and the squared sign in there. Okay, so say that g of x is 2x minus 1, and I want to know what the composite function f of g of x is. Well, this, my first step, normally I write this, that's the same as f of g of x. So if I follow the same routine as before, I'm going to take f of x, and wherever there is an x in it, I'm going to replace it with 2x minus 1. So this is going to be 3, 2x minus 1 squared plus 2x minus 1. Now I'm not going to leave it like that. I'm obviously going to expand it and simplify. Please make sure you do not put this as 4x squared minus 1. You need to remember that's 4x squared minus 4x plus 1 plus 2x minus 1 on the end, which equals 12x squared. I'm going to simplify, minus 12x plus 2x minus 10x plus 3 minus 1 plus 2. That's f of g of x. G of f of x, so the order is really important, okay? Here we've got g of f of x. So again, think about, I would automatically write this. So wherever there's an x in g of x, I'm going to replace it with this. So it's a bit easier to do this one. So it's 2, 3x squared plus x. Minus 1 on the end, isn't it? So 6x squared plus 2x minus 1. If you see notation like this, f squared x, that is the same as f of x. Hopefully that makes sense to you. So that's the same as, obviously, f of x, which gets a bit fiddly. It's 3, and so wherever there's an x squared in here, I'm going to replace it with this. Very bizarre. Plus. Not much practical applications, but it does sometimes come up. And that's, in a nutshell, composite functions. Here we almost have to work backwards. So the functions f and g are defined as f of x is 1 over x, g of x equals 2 over x. And I want to write those functions in terms of f and g. Well, 1 over 2x, well, hopefully we can see that in that case, 2x has been slotted into that point here. So that's the same as f of g of x. For part 2, well, 2 over x, hopefully I can see again that means we've taken this 1 over x and put it into here, because that'd be 2 times 1 over x, which is 2 over x. So that would be g of f of x. And finally, part 3, well, hopefully I can see I've got x has been multiplied by 2 and then multiplied by 2 again. This is the only function involving a multiply by 2, so it's g of x, or more neatly g squared x. Right, we're going to crack right on and do inverse functions as well. So please write this down, pause the video if you need to take anything down. So inverse functions, again, something you've done before, I'd imagine. The inverse of a function undoes the effect of the original function or the function. That obviously makes sense. The word inverse is in there. We know what inverse means. It's basically the opposite. What's going to help us with this is the graph of the inverse function is a reflection of the graph of the original function in the line y equals x. That sounds complicated. We're not going to use that massive amounts. It's a fact you should know and you need to know. However, it can more importantly be really useful in checking our answers. So this is something new that kind of uses what we used last lesson. We learned last lesson. For a function to have an inverse, it must be 1 to 1. Okay, it must be 1 to 1. We can find the inverse of a many to one mapping, but it's not technically going to be a function, so we would say it's not got an inverse. Okay, so for a function to have an inverse, it must be 1 to 1. This bit here, kind of, this middle section here kind of helps us, because if I've got some sort of function, like a parabola, right, and say I was to reflect that in the line y equals x, so that we know that that's the line y equals x. So if I was to reflect that in there, and I should get something, oh, I'm not going to be able to do this now because, alright, okay, that's rubbish, but you get the gist. So say that it would turn something like that. Well, straight away looking at that green line, you should know that that's not a function. That's not a function because we've got a one to many mapping going on here, and we know that functions are either 1 to 1 or many to 1. So important, keep it here, and it might just be a 1 mark question, like for example, why doesn't have it in it? Why doesn't it have an inverse? Something along those lines, right? So for a function to have an inverse, it must be 1 to 1. Right. And here is how to find an inverse. So here's a question: f of x equals 2x cubed plus 1. We want to know the inverse. So that's the sign for an inverse function. And this is how we do it. So step 1 is, for me, the way I do it. So we've got f of x equals 2x cubed plus 1. F of x is a bit more difficult to deal with, or it's a bit fiddly, so I'm going to change that f of x to y. So y equals 2x cubed plus 1. Now I'm going to rearrange it to make x the subject. So take one away from both sides. So it's all old school rearranging skills. And I'm going to divide by 2. And then finally, I'm going to cube root both sides. And then the last step, once I've done that, I've made x a subject, I swap the x's and y's, which sounds like a trick, and it basically is a trick. All right, but I literally just swap the x and y's in. So for this case, the inverse function is cube root of, so I just replace that y with an x, and that's it, done. So the steps are, remember, replace that f of x with a y, rearrange it to make x a subject, and then just swap the x's for the y's for x's. The reason I said about this being useful is because now there's a good way to check it. If you were to draw the graph of this in your calculator, and you draw the graph of this in your calculator, you should be able to see that one is a reflection of the other in the line y equals x. If you get things that do not look like a reflection, then you know something's gone wrong with your inverse. Right, one last quick question. So we've got two functions here. Question 1, we're going to come up with an interesting result here. What is the range of each function? Well, f of x, think about what's going to come out of that. So if I've got the graph, notice that it's been restricted here. So x is greater than or equal to 0. So it's going to look something like this. It's like half of a parabola. And that's minus 4 down there. So the range of f of x f of x is always going to be, the lowest it can be is -4, so it's always greater than or equal to -4. For g of x, again, this graph is going to look something along these lines. So g of x, the range, the lowest that's going to possibly be, the lowest square root I'd ever have would be 0. So it's going to always be greater than or equal to 0. So those are our two ranges. F of x, that's a range for f of x, that is a range for g of x. Right, let's answer these next two questions. Well, without too much work for part 2, we can work out that the inverse function is the square root of x plus 4. If I think about the domain, so what can go into that? Well, for us to be able to square root it, it has to be 0 or positive. So for that to happen, x has to be greater than or equal to -4. Hopefully there we can see that there's very much a connection here to this part. Now, let's just think about the graphs and why that would be. If I've got the graph here, well, we've already got it, of f of x, well, we already know that when you find the inverse, it's the same as reflecting that line in y equals x. Now, if I was to do that, I would end up with something that looks like this. It's a bit dodgy, but it's something that looks like that. Well, the domain there, clearly that point is going to be -4 again, because I've reflected it in y equals x. So the domain is -4 and anything along here. So that's why we come up with this important result. Please write this down. The domain of the inverse of f of x is the same as the range of f of x. And this is a really useful result. If I didn't know that, sometimes when we work out the inverse and we talk about its domain, we come up with unusual results because we haven't considered what could have originally gone into this function. So it can get quite fiddly. So for the next one, I can work out without too much difficulty that the inverse function of g is x squared plus 3. You think that the range for that, sorry, the domain for that is going to be all of R. We can put anything in there because we can square it and add 3. However, we need to bear in mind these restrictions that we had at the start. And it can get quite confusing. However, if we use this, that the domain of the inverse is the same as the range of the original function, I can just go straight away that x is, I can use this here, so x is greater than or equal to 0. Similarly, if I think of the range of those two inverse functions, well, the range of this here, well, x, the range is always going to be greater than or equal to 0, which is the same as the domain of the original. And for the other one, you can probably guess what that is going to be. If I think about the range of this, well, it's always going to be greater than or equal to 3, which oddly enough, again, is the same as the domain of the original. So these kind of work hand in hand. The domain of one function is the range of its inverse and vice versa.